It is a pleasure to welcome you to second edition of the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is a pro bono initiative led by Dr. Partha Mishra and Professor Sarat Das. Initiated in 2020, it is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. Today's lecture is on soil erosion, which will be delivered by Professor Jean-Louis Briord and Mr. Amir Shahkolahi. Amir has a bachelor's and master's degree in civil engineering. As a designer, project manager and researcher, he has been involved in civil and geosynthetic industry over the last 20 years. He is the technical manager for Australia and New Zealand at Global Synthetics. Amir is the vice chair of the Australian Geomechanics Society Queensland chapter, member of the International Geosynthetic Society Technical Committees for Reinforcement and Stabilization, board member of the American Society of Civil Engineers Australian section, member of the ASTM Committee D35 on Geosynthetics, industry board member of the Australian Pavement Research Hub, board member of ARC Training Centre for Advanced Technologies in Rail Track Infrastructure, and member of the Standards Australia Technical Committee CEO32 Reinforced Fill Structures Working Group. He is also a board member of the International Geosynthetic Society Technical Committees for Barriers, board member of the QLD Landfill Working Group, board member of the Waste Management and Resource Recovery of Australia in QLD, guest lecturer at Sunshine Coast University and University of Wollongong, part-time PhD researcher at Queensland University of Technology, and the industry supervisor and advisor for several geosynthetic research projects in Australia and overseas.
Okay, good morning, good afternoon, good night, good evening, everyone. Thank you very much for inviting me to this lecture. It's a great pleasure to be here and to be with you guys, and especially be in this session with our ASCE chair, John Lewis. And let's start the presentation. Thank you for the kind introduction. This presentation is focused on the controlling erosion. It was a wide topic if you wanted to talk about controlling erosion in all areas. So I try to focus on drainage channels and specifically focus on new technologies and geosynthetics. Otherwise, we needed a half a day or 1 day to cover all things. But I try to touch other aspects a little bit. The source of water erosion can be different things. The type of water erosion, it can be a raindrop erosion because of rain. It can be sheet erosion. It can be reel and gully erosion, or a stream and channel erosion. We are not talking about what are these types, how these happen. We are assuming that we know about the type of erosion, and we are mainly talking about water erosion. Of course, we know that wind can be also a source of erosion in lots of areas, and in some areas it can be even more critical than water erosion. But mainly in road applications, for example, we are talking about water. So this presentation is more focused on water erosion control. Every year, we have about 6.5 million metric tons of solid material going into natural waterways. And for example, in Australia, rate of soil erosion now far exceeds rates of formation of the soil, in factor of several hundreds. And this is not good. And to be honest, most of this is happening in Queensland, actually, to be honest. US EPA estimates that sediment deposition in reservoirs from stormwater runoff cost up to $500 million annually to get rid of. And of course, EPA suggests that vegetation is one of the best ways to control the erosion or sediments and pollutions. This is what can happen easily if we don't control sedimentation and erosion. And all this can go into our waterways, and this is what we want to avoid. Now, the effective erosion control principles and what we should follow and consider to have a good erosion control system can be summarized as reducing the erosive forces as much as we can, increasing the resistance forces, applying good erosion control techniques, modifying the topography if we can, limiting the exposure of the soil by covering the soil with different techniques that we will talk today about that, keeping runoff velocities low, and inspections and maintenance. These are the main principles that we should consider when we want to design an erosion control system. Now, we can have two different ways of controlling erosion. We can have a defensive system. It means, okay, when it is eroded, now let's keep it somewhere. It is good, at least we keep it from going into waterways or roads, but still the erosion is happening and we are losing the soil. So the better way can be offensive system. So stop the soil from getting eroded. This is better way if we can do that. If you want to, let's say, classify the erosion control based management practices, we can have two different things: source control or runoff control. Source control, as we said, it's like a offensive system. It's protection of exposed surface from erosive energy. It can be rain, it can be runoff, and this is mainly by covering the soil by an erosion control material. If we cannot do that and we cannot cover the soil, then we can go to runoff control systems or BMPs, sorry, which means considering, for example, modification of the slope, reduction of the slope gradients, controlling flow velocities, and these sort of techniques that it's actually trying to avoid erosion by these techniques. But let's focus on the source control, which is covering the soil and the surface of the soil by erosion control materials. Now in channels, FHWA or Federal Highway Administration, they have categorized these systems for channels to two: rigid systems and flexible systems. Rigid systems like concrete or asphalt, for example, or stone masonry in interlocking blocks, and similar applications. These are good and they are rigid and they don't get eroded. But of course, because they are rigid, there is a risk that if something comes to the foundation, then they will have cracks and fails. The flexible system like vegetation systems, riprap, gabion mattresses, or silver confinement, or hydromulching even, which is a kind of covering but not permanently, and RECPs or road erosion control products. Another classification that doesn't matter which one we use, which technique we use, we can have a temporary solution or permanent solution. Temporary solution is to controlling the erosion temporarily, because in the meantime and after the construction is finished, the source of erosion is gone, so we don't have any erosion anymore. Or we want to control the erosion in the meantime until vegetation grows. So after vegetation grows, we rely on vegetation to take care of erosion control. The permanent solution is when we have permanently the risk of erosion. It can be whether we cannot have vegetation or vegetation alone is not enough to control the erosion. So we think of using something permanent to control the erosion. Now they have different techniques, as we discussed: concrete, rock, silver confinement, gabions, erosion control blankets, TRMs, concrete blankets, different things. Which one we should use? All of them have their own benefits and they have their own limitations. If we know the benefit and limitation of each system, we can choose the one that suits us. These are the considerations that we should consider when we want to design or select. What is the source of erosion? What's the cost? Is it permanent or erosion or temporary solution that we want? Safety during construction, operation and maintenance, environmental considerations and carbon footprint, hydraulic conditions, is it a very low flow rate or high flow rate, durability and long-term, and many more. For example, hard armoring solutions like rock, gabions, and concrete mats, these are good. They have a very long history. The comfort level is okay. The cost can be high. Sometimes the availability of the rock can be a problem, and it's not easy to install this. Maintenance is moderate to high, sometimes even low. If it is like a growth rock, they just leave it there, but it needs some maintenance. Environmental, the carbon footprint can be high, and we are using the source of the rock, and the water quality is not very beneficial for water quality because it's just the water runs on top of that. It's most of the times not permeable unless we use something like rock mattresses and not growth rocks. A newer category, which is not very new, but it's newer, is road erosion control products, or RECPs. RECP is a general name. I'm sure all of us have heard of these products, but with their own names, not the general name. So RECP is a general name that we give to this family, let's say. They can be products made of natural or synthetic fibers. They were introduced late 1960s, and then from 1990s they became an acceptable method after EPA in US had some technical notes and a lot of documentations about these solutions. Now let's go through them. The RACPs can be temporary. The temporary RACPs are like mulch control netting and erosion control blankets. So we have seen them. All these blankets that we see, they are mainly two-dimensional and they are temporary. Why they are temporary? Because they are not UV stabilized. So they are only there until the vegetation grows. After the vegetation grows, we rely on the vegetation because these can happen easily with these products. So they are not UV stabilized. Between few months up to 1 year is what we expect to the design life of these. And then after that, we have vegetation. So we use these products as a temporary solution, and when we can rely on the soil by itself or vegetation to take care of the erosion. So erosion is efficient, vegetation is efficient, but there's problem. Vegetation also has some problems. When we have above a certain level of erosive forces, which John discussed very well today, even vegetation may not be enough to control the erosion for us. So what is the solution here? Traditionally, we used to go to rock when vegetation cannot work. But there is another solution. The solution is to reinforce the vegetation, reinforce the roots. So we make it a reinforced vegetation. For this, we use a permanent RACP, which is called turf reinforcement mat. Again, these are all generic names. So turf reinforcement mat, or TRM, they are the geosynthetic material mainly made of UV stabilized synthetic products like polypropylene, because polypropylene is very durable with some additives against chemicals and these. So they are 3D, not 2D. They are three-dimensional. So we have an interaction between soil and roots and vegetation to these products. And as you can see in the photo, it reinforces the vegetation. So it becomes reinforced vegetation. Now this vegetation can withstand higher shear and velocity forces. We have normally two TRMs, two types in the world. The normal TRMs, which are moderate UV stabilized, and the tensile capacity is less than 44 kilonewton. When we go to higher tensile capacities, more than 44 kilonewton, according to FHWA, and the very high UV stabilization, like up to 75 or 100 years, then we call them high performance TRM or Hptr. So these are, again, general descriptions. They are very easy to use. As you can see, it's just rolled. It's like a blanket, pinned, and vegetation grows through it, and it looks like a natural vegetation after it's vegetated. So it's like a natural vegetation, but reinforced. Some application of this system I want to show you here. For example, these are real projects in different parts of the world. As you can see, it's being used. You can combine it with rock or concrete or use it by itself, depending on the hydraulic condition of the site. And you can see it's, for example, for bank or pond remediation. All these areas are reinforced vegetation. They are not vegetation alone. So that's why they can withstand all these hydraulic forces. We can have levees and dams. We will talk about this a little bit more. We can have a slope stabilization. So all these nice vegetations that you can see, they are reinforced with a TRM. So to summarize what we should use, normally when we have low shear and velocity forces, let's say, we can use normal solutions. So we rely on vegetation. That's why we use just the soil or hydromulching or erosion control blankets, because all of them are natural vegetation. Now, when we have high velocities or high shear forces, we have to use rock or concrete or hard armoring solution or riprap. Between these two, there is a gap. Traditionally, we used to use rock again here as well. But to be honest, it is very over-designed and conservative because we are using a very high, let's say, solution for something which is moderate. This is where the word came into consideration that, okay, we in this range, in the middle, we can use reinforced vegetation. So here is where we can use reinforced vegetation. Above a specific value, still we need some hard armor solutions, but in the between, we can use a sustainable replacement. This is now being accepted as a sustainable replacement for rock and concrete when we have acceptable shear and velocity. Now, why do we say it is sustainable replacement for rock? to investigate the sustainability. There are two main components, which is the cost and also the carbon footprint. It is just a very general comparison. It can be different in different countries, different locations, but it was a comparison that we did some years ago in Australia. And we checked with the United States. Turf reinforcement mat versus riprap versus concrete. So you can see the cost is very, very different, and it can be much cheaper where applicable. Carbon footprint, this is a project that we wanted to cover about 70,000 square meters of an area to control the erosion. It is in the United States. The solutions that we had was rock riprap, concrete, and TRM. To cover that area for rock riprap, we needed 5,100 cubic meter of rock. For concrete, we needed 2,500 cubic meter. Now, these are the trucks that required to deliver those amount of products or material to the site. The distance to the site, we considered TRM has the highest distance, 800 kilonewton. But still, considering all of these, because of the number of trucks is only one, the total shipment to the site for TRM is only 800 kilometer. For concrete and riprap is 10,000 and 53,000 kilometers. That's why in the bottom you can see the emission reduction that we could see, we could get for TRM is very low. So this is the emission that was produced, the total emission produced in the project by using TRM. So that's why we say wherever we can use TRMs as a replacement for rock, it is the suggestion to do that because it's a good solution. Now, how can we measure or model the performance of TRMs in a channel or a slope? There's a standard test, full-scale flume test. This is the only performance test. Other tests like raindrop, or there are other tests, but there are index tests. This is the only performance test that we have for TRMs with vegetation, without vegetation, and this ASTM, they have their own criteria. This is the test set up in Colorado State University that they can simulate average discharge as high as 370 liter per second per meter. And they make the exact solution. It can be a TRM, it can be rock, it can be concrete, whatever. And they put it in this flume. I have a short video to show you how it works. So this is the setup, and now they let the water go on top of that, and by this they measure the amount of erosion. This is what they do. This graph shows a very nice comparison between rock and Hptr. So there are different things that we can get from this. First of all, the size of the rock, D50, 50 centimeter, 30 centimeter, 60 centimeter, and 90 centimeter. On the horizontal axis in the bottom, you can see the gradient, the slope, and horizontal axis on top, the vegetation condition for the TRM. So the first thing that we see that the amount of vegetation can affect the performance definitely. The higher or the denser the vegetation, the better performance we get from TRMs. Of course, they can be used without vegetation as well, but the performance is different. Now, as you can see in this graph, for example, if we compare the TRM with D1590 centimeters, which is 900 millimeter rock, it shows that when we have more than 60% of vegetation, Hptr works even better than rock with 900 millimeter diameter. For the values less than 30% vegetation, or let's say more than 30% vegetation, the Hptr works even better than 600 millimeter rock. So this gives us a nice comparison between rock and TRM. Of course, this can be different for different vegetations, different rock. This is just, it's not applicable to all conditions, all TRMs. It is not a design chart. It's just a comparison performance for shear values. And why we say shear, as John also mentioned, we always design for shear because velocity is not a good thing to design. We design for shear values. How do we design? this is a very simple design procedure for designing with TRMs on channels. We follow the HEC 15. HEC 15 is the hydraulic engineering circular number 15 by US Department of Transportation, HWA, and it's design of roadside channels with flexible linings. The design criteria is very, very simple. We have a maximum shear stress on the channel bed, which is TD, and it's very standard calculation. And then we have the permissible shear stress on the channel. As long as the permissible shear is more than maximum shear multiplied by safety factor, which is normally 1.3, we are safe. So this is what we design for. Now the question is, we know what can be the maximum shear stress on the channel bed by knowing what's the soil type. But what is the permissible shear stress? Again, the equations are available in HEC 15. If we have bare soil, no vegetation, for fine-grade non-cohesive soil with D75 less than 1.5 millimeter, it's relatively constant, and it's considered as 1 Newton per square meter. For coarse-grained non-cohesive soil, we can use this equation, which is alpha D75. For cohesive soil, the basic equation is, as you can see here, which is the PI of the soil comes into consideration, the plasticity index, and we have some coefficients that we can find out in the references. So as it's very obvious, the type of the soil affect the permeable shear stress, which completely makes sense. Now, we first check the bare soil without any vegetation. We calculate this and we check if it is okay, and if it is more than the maximum and it's okay. If not, then we go to vegetation alone without any reinforcement, just vegetation. Now, equation number 2 is the permissible shear stress just for vegetation. And there's a factor called C or CF. C here is the grass cover factor, and NS is the soil grain roughness, and N is the roughness or manning factor. So this is very important. For reinforced vegetation, the equation is exactly the same. The only thing which is different is the C factor and N. So when we use TRM or Hptr, the C factor and the N will be changed. Because of that, we have a higher allowable shear stress. That is how it works. And that is how we can calculate the allowable shear stress. Or we can also use the other way, we can use the flume test. Just to give you an idea of the difference between manning factors. For rigid solutions, lining systems, or online, like bare soil or RECPs. We can see for concrete, for riprap, for asphalt, for bare soil without anything, just soil, for erosion control blankets or open weave textile, which is the temporary RECP, and for turf reinforcement map. These are just roughly, and it's a range, so it depends on the vegetation as well. So another way to calculate the allowable shear stress is the flume test that we already discussed. By this, they can determine what's the maximum shear stress that they can get, allowable shear stress from the specific material. Now, to go to the case study, it was a project in Australia, in Queensland. There are many projects. I just chose this one because it is very interesting. The original design was with rock gabion mattresses. So it was rock mattress design, and it was designed for waterway of 1 in 100 years peak flow. And as we can see, these are the dimensions of the channel. 5 meter wide in the base, 2% side, the channel slope, and side slope 1 to 4. The length 300 meters, flow depth 1.2, and discharge was about 9 cubic meter per second. Now, they came to us and asked us to redesign it with TRM and Hptr solutions to see how does it change the cost. So what we did, we used the Hptr. These are the values that we had in the Hptr. It was highly UV stabilized for 100 years. The resiliency was 80%, the light penetration 10, and the tensile capacity 44. By changing the design from rock mattress to Hptr, we saved them about 50% of the cost and time, which is a huge saving. I will show you the design values. This is the original design. We redesigned it, and we checked actually the safety factor. We realized that by the current situation that they have, the safety factor that they get from rock mattress is 17. As an engineer, we know that it is very, very, very high and conservative, and you never design for safety factor of 17, especially for a channel like that. So we check with Hptrm, even with Hptrm that we design, still the safety factor is 5.9 with vegetation and 3.4 without any vegetation. So even if they have only Hptrm with no vegetation, still the safety factor is 3. That is how we could save them a lot of money and still be conservative, I would say. So these are the construction procedures. They put the material, hydroseeding, put the Hptrm, and then it's vegetated. It looks like natural vegetation, but it's actually a reinforced vegetation. Now, what are the applications that we can get from these technologies? I told you that it's mainly channels, but I just show you a few slides about the slope as well. The slope erosion control can also be considered by using TRMs and Hptrm. How we design for slopes is very simple. We use the same equation that we use for slope, Rossley or Rossley 2 equation. This is the same that we use for TRM or without TRM. The only difference is that when we use TRM, the C factor changes, which is the ground cover factor. So when we use the TRM, the C factor reduces. So that's why we can have less soil loss. So this equation gives us the amount of soil loss. A is the annual soil loss. And by using TRMs, we reduce this soil loss, which is what we like to have on the slopes. Now, to give you an idea about different C factors, this is the bare soil. When we have temporary vegetation, when we have hydromulching, when we have erosion control blankets, and when we have TRM, it's less than 0.01. They are just very typical values. Another application is when we have erosion control, but also we have some superficial stability. So some it's a typo, slope failure. So we have shallow failure in the surface. It's not global stability. It is just the superficial stability, let's say up to 3 meters deep. These are the situations that we can also control by these systems. What we do with a traditional solution is let's use rock, replace it with rock, or this rock hopefully will protect the erosion and everything. Another solution is exactly the same that we discussed, just by adding a anchorage. So we call it engineering earth armoring system. Engineering earth armoring system is a Hptrm plus earth anchors. These are the flexible anchors. So it becomes this, so like that. They put the Hptrm and then insert the anchors to the soil and then pull the anchors. And these anchors become like a system that keeps the soil together. And this pyramid effect, let's say, keeps the soil together and at the same time controls the erosion on the surface. We also will do pull-out tests on site to check the anchors which is installed, and it's very easy to install this. Just to show you an idea of what it looks like, they put the Hptrm, pin it, and then push the anchors into the soil. When we pull the anchors, the anchor head turns, as you can see here, and then lock the soil. And that is how we provide the surface stability. To give you an idea, it's one of the examples that we did in the United States. We have more examples in Australia and worldwide. It's being used worldwide. This was the situation that they had, and you can see the constructions on top. So they wanted to protect the slope. We did some modeling for them without any anchorage, without anything. The safety factor was 0.9. When we used this anchorage system and Hptrm and anchorage, we could increase it to 1.5, 1.6, which is acceptable. So that's why they use, you can see they put the mat, then put the anchors, then say pull the anchors to become locked, and then it's vegetated after 2 months. So it looks like natural vegetation, but it's actually, the erosion is controlled, the stability is also fulfilled. Levee overtopping, it was a nice discussion by John today about levees. That's why I added to my presentation, to be honest. So I cheated on John's presentation, but I realized it's very interesting because he talked about the project that was actually the start of a very, very good research by U.S. Army Corps of Engineers. So overtopping of levees can cause erosion on the downstream or downside of the levee. These are the traditional ways of making levees. This is one of the very, very early levees in the early days that they used to make levees like that. But now there are different armoring systems to protect the erosion on the levees. It can be just vegetation, hard armors, concrete rocks, or concrete blankets, or rocks, whatever. But another solution is the same that we discussed previously, which is, again, engineering earth armoring system. So as you can see in the photo, on the land side or upstream, they use the same technology to protect the erosion from overtopping. Here, we definitely need the anchors as well, the anchored system. So this is the background. Today, we heard about the Orleans flood in 2005 because of the hurricane that occurred. This was exactly the start of a very huge research with very many years research that ended up with finalizing a system for levees. So it's a very short background. Approximately 80% of the city was flooded, and flood depth exceeded 15 feet. And wave caused 50 major levee breaches. And you can see it was a disaster, and more than 1,500 lives were lost. Some of the issues that they face, it is the downstream of the levee and the erosions that happened because of these cyclones. So what happened in 2006, U.S. Army Corps of Engineers started $14.5 billion program, and it's called Hurricane and Storm Damage Risk Reduction System. The goal was to see what is the most cost-effective, environmental friendly, and high-performance solution to control these erosions and control levees, erosion or armoring the levees. The background, and in 2005 and 2006, they, as a trial, they used this earth armoring system on a levee called Penn Flood Levee as a trial. So what happened in 2005, 2006? It was installed. 2008, category 3 storm with 200 kilometer per hour flood occurred. That was a disaster. What happened to Penn Levee? Nothing. So it survived. So real condition, real full-scale trial, it showed that the EEAS or engineering earth armoring solution can work and can protect the levees from damages in hurricanes and storm. So that's why they defined a research project at that time based on this experience in Penn Levee, a two-phase research. Phase one, a full-scale field test and field trial to investigate what are, they realized that the Hptrm, the anchoring system, works. Now they wanted to see what are the requirements, what should be the properties of this Hptrm, so they can withstand loads, debris, mowings, all these loads that can occur. Phase two was a full-scale overtopping test to investigate now what is the performance of this system. Do they really work? They can model it. So phase one, 1.5 kilometers of levees were used for this research. And this is the installation. They used different systems, many different systems, including the ESS. And then they tried to drive on top of that, do the mowing, all the natural, everything that they could happen. And the phase two was, again, full-scale overtopping test, exactly the same that we see in Colorado State University. They did the same. And there's a short video that tells us about that experience, which I will play here for you.
Well, what we've done is brought the ocean to Colorado. We're looking at simulating wave overtopping for levees. Having the most landlocked state of the union, it's quite a feat to be able to build the world's largest wave simulator, overtopping simulator here at CSU. What we do is through the tank, the green tank that we have above us, hold a volume of water. So we release that volume of water at a given rate for a given period of time so that we can simulate the waves crashing over the top crest of a levee and then accelerating down the backside. This is the ocean or a large lake on our levee. We're not simulating the frontal protection. We're looking at what happens on this protected side of the levees, where that erosion occurs, how quickly it moves through the levee, breaches the levee, and then the system fails. So as the waves form in the ocean, they hit the levee, crash across the top, and accelerate down the backside. We're simulating that depth and velocity at the crest through a tank that sits above the levee.
Based on Katrina, we saw that there were a lot of various levee failures, and so now we're trying to go back and figure out why that happened in more detail, and also what we can do to prevent that from happening in the future.
So what we've done is constructed for this year for Jacksonville Corps of Engineers 2 large greenhouses, 2 60 by 90 foot greenhouses that we can completely temperature, humidity, and UV control. so that we can simulate the growing conditions essentially in any part of the country. So we're able to look at a lot of different types of protection materials, bare soils, concrete blocks, vegetation, engineered vegetated systems, a lot of different tools that we have available to us as engineers and designers then to protect this backside and provide the public safety that's required for a given storm condition.
We're going to be looking at the aeration of the flow and trying to see how density changes of the water along the levee. And then we're also going to be looking at what the forces are at the toe of the levee to see why exactly we were getting failures with the other tests that we ran.
So there are lots of results published. Just show you one of the results that, for example, it is test duration versus the overtopping volume, the cumulative, and shows the duration versus damage with different systems that they have, TRMs, Hptrms, different types of TRMs, and even blocks. There are other graphs that I didn't show here. It's in the paper that I presented last year, and another paper that I presented this year. They are available. I can send it to you, more details and references. What are the results? Comparing different blocks, even concrete blocks, so all of them are available. And based on that, they develop a guideline. And it's now being used in more than 3 million square meters of those areas. New Orlando, they are using this armoring system, engineering armoring system, which was found as the sustainable solution to protect the levees based on all these tests. And it's summarized. You can refer to this book. It's a very nice book. You can have a look and get more idea about what's happening and the summary of what's happened there. By this, I want to end my presentation for today. We can talk a lot more about coastal protection and other type of protections, but I think I'll leave it here so we can go through any questions if there is any. And I want to have my acknowledgement to our friends at Propex United States, AST, especially Australia and New Zealand chapter, and Global Synthetics, and all other people. And again, thank you guys for inviting me to this presentation. It was a pleasure. If there's any question, I'm more than happy to talk about. Yes, there is a question that I can answer. How can we estimate the longevity of Hptr in years, knowing that the system, once installed inside, is going to be subject to ongoing shear forces? That's a very good question. The main criteria that we consider for designing Hptrms about the lifetime is the UV stability. And it is a standard ASTM UV test that we consider. And we test it normally 500, 1,000, 3,000, and 10,000 hours. And we say, okay, if you test it for 10,000 hours, you're almost simulating between 75 to 100 years in real life, because these are accelerated testing. And that is how we take care of the lifetime durability. This is the main durability test for Hptrms. And that's why in FHWA guideline, they say if you are working with high flow or high velocities or high shear values, your Hptrm should be more than 45 kilonewton per meter. It's to make sure that it takes care of all these things. But of course, because there is shear forces, there may be creep, there may be other things happening. It's a very, very good and right question, but at the moment, it's not considered as a performance criteria. There's another very good question that they asked that I actually had these slides. I can bring it because I didn't know about the time. These TRM or Hptrms can be used without vegetation as well, or they can be used with artificial vegetation. Yes, we have had some situations, for example, in dams or semi-arid areas, that they even use them without any vegetation. It can survive because if it is a Hptrm with 7,500 years design life and test results. Or we use it, for example, in sandy area when we put artificial vegetation and it's somehow covered. That's why we have 10% up to 100% coverage. We put grass, let's say, grown grass on top of this. So they can be used with any type of vegetation. There's no problem with that. If there's any more thing required, please send me an email, and I'm more than happy to send you a lot more information on that. At the maximum slope, theoretically and technically, you can install the Hptrms in any slope. Your photos that I have, it's like 70, 80 degrees. The main thing is about vegetation. What is the slope that you can have vegetation? That's the main thing. You cannot have vegetation. If you can have vegetation on 80 degrees, that's fine. Because these TRMs or Hptrms, they reinforce the vegetation. So there should be a vegetation to reinforce it. That's why some people we have seen some projects that they design with these products, but they don't think about vegetation. They just think, okay, it should grow. No, we need soil, seed, irrigation system. So it's more about, let's say, vegetation. Of course, the armoring system. We normally say 45, 50, 60 degrees. It depends on the stability of the surface. So if it is going to the slope stability, surface stability, we model it to determine. But normally, as I said, it's mainly the vegetation is the criteria.
Okay, so there's one similar question that maximum slope for the geocell type of protection.
Geocell, I will not go more than 1-to-1, to be honest.
Yeah. Because
with geocell, there is a problem that the soil inside the cell will be protected, that's fine, but the soil inside the cell can move inside the cell. So I will not go more than 1-to-1 for geocell. And the type of vegetation, you can have any type of vegetation. Actually, when we model the TRMs with vegetation, we can choose what type of vegetation we have. It can be grass. Even some people use bush, for example, vegetations, or even they put trees, they cut it and put trees. So you can have any type of vegetation. I have photos with different types of vegetations. Yes, that's a very nice question. I can send you some more information. If you can please send me an email, my email is on the monitor, then I'm more than happy to share some information in regard with you, definitely. Sandy erosion, yes, we can use it in sand. Again, I have some photos that shows these are being used in sand. Yes, as you can see that this system on top is with vegetation. In the bottom, it's actually a dam, downstream of a dam. It's a Hptr without any vegetation. And of course, there is a geotextile underneath in this case. So it can be used in both cases. And the other photo is sandy area. So you can see it's a sandy beach. And it is being used, the TRM, and then some vegetation, which is the local vegetation, is being put down there. So yes, it can be used. And just we need to design for that. We need to know what is the type of the vegetation that you have, what's the length of the anchor. So in different applications, yes, it can be used. But the main maintenance is mowing the vegetation. So when you have vegetation, you want to have mowing, and it depends on the type of vegetation you have. That's why in Colorado, in the US Army test, they tested for real mowing loads. And there's a parameter called resiliency. Resiliency is the parameter or the property of TRM or Hptr that takes care of the mowing and all these loads. So the TRM should have a high resiliency. And there is normally the different TRMs are available. Some of them, they have geotextile, some of them they don't, but you don't need geotextile, because if you put a geotextile, then vegetation, you're making it difficult for vegetation to go through that. So the main idea of TRM is to let vegetation to go through that. So I haven't seen the permanent TRMs with geotextile to work very well, unless there are some seeds inside the TRM encapsulated or something like that. As I said, there's no non-woven geotextile. Sometimes we use a non-woven geotextile under the TRM, it is the case that we don't want to have vegetation. And thank you everyone for joining this webinar, and thank you again for inviting me to this webinar.